Okay, thanks. So this is joint work with Shai, Shalev-Shwartz and Eran, Tromer from Tel Aviv University. And this talk deals with maybe the two most basic resources that we deal with in learning, namely sample complexity, how much data we need in order to learn, and computational complexity, how much time do we need in order to do the learning. Now, both resources have, of course, been considered, but maybe the classical viewpoint is to give more emphasis to the issue of sample complexity. So how can we learn even if we get very little data? So, like if you look at the average UCI data set for 1990, maybe you had 500 examples and you had to learn based on that. But in many of the current applications of machine learning, actually getting a lot of data is not that much of a problem. It can actually have huge amounts of data, and the problem is really not the amount of data, but more the computation time, whether you can get a reasonable result in some reasonable time. And the main question is, how do we make this time as small as possible to get, say, some given accuracy? This kind of question also has some qualitative implications. So if you look at how most learning algorithms behave, usually the runtime increases with the amount of data. So maybe we can get 10,000 examples and run the algorithm for 1 hour and get a predictor with 5% error. What we can do instead is, if we're in one of these applications where we can get a huge amount of data, maybe 1 million examples, and really run our algorithm for a very long time, say a week, and finally we get a predictor with 4.98% error. And of course, this can be important if you really care about the 0.02% improvement. But if you're fine with 5%, then of course you can always just subsample, just take 10,000 examples and get 5% in 1 hour. But an interesting question here is whether you can utilize the fact that you get a lot of data to actually reduce the runtime, to get a 5% predictor in less than 1 hour. Now, this idea of using more data to do less work has been explored earlier, particularly in an ICML 2008 paper by Shalev-Shwartz and Tromer, which actually got best paper. That was specifically for learning support vector machines, and they attempted to show this kind of phenomena, but that work had also some limitations. So first of all, the kind of improvement that they showed was just a small constant factor. And the second thing, it was just based on upper bound. So they showed that for a certain sample size, there's some upper bound on the runtime. And for a larger sample size, there is another upper bound which is somewhat smaller. But this doesn't prove that there is really a trade-off here. It's just an upper bound. So in this work, we improve on that in two respects. So first of all, we show a learning setting where there is a provable improvement in performance as a function of the amount of data that you get. And we also discuss various realistic learning settings where there seems to be a significant runtime improvement by more than constant factors. So the one with the provable improvement is a bit artificial. The realistic learning settings are realistic, but they are based just on upper bounds. Okay, so the kind of model that we focus is a very standard agnostic pack style model. So we assume that we get as input some training set of labeled examples, xi, yi. We have a learning algorithm which applies some learning rule on this training data, and it tries to learn with respect to some hypothesis class H, and the output is some predictor, some mapping between X and Y. Now we're going to focus on an agnostic setting, so we're not going to assume anything about the distribution from which the training data come from. Particularly, there doesn't have to be some particular hypothesis which perfectly labels all the examples. It's just some arbitrary distribution. The second property is that we'll focus on improper learning. So the predictor returned by the algorithm doesn't have to be in the hypothesis class H. It can be any sort of function, which is a natural assumption in learning settings where we just care about eventually getting a good predictor. And our goal in this setting is to indeed find some predictor H whose expected error is epsilon close to the best possible error you can get in this hypothesis class. Okay? So one common technique that we'll see in order to get this kind of behavior algorithmically is the following. So maybe our hypothesis class, H, is reasonably small, you can learn it, but it has some hard structure, some, say, combinatorial structure, which makes it hard to find the best or close to best hypothesis in this class. So what we can do instead is to enlarge this hypothesis class, replace it by some larger class H tilde, which has a simpler structure. It's easier to, say, optimize over this class. So we have a trade-off here. On one hand, it would be easier to find a good H tilde, a good hypothesis in H tilde, but because the class is larger, we also need more data to statistically learn with respect to this class. So we'll see examples of this later on. So just to give one very simple and concrete example, so we're going to look at a very simple ranking problem where your instances are just pairs of numbers between 1 and d. So you can think of them as, say, two objects. And your goal is to predict whether object I is preferable over object j. The natural hypothesis class for this problem is just a set of all permutations, so all possible rankings of these d objects. And the loss function is just the 0, 1. So we get a loss of 1 if we mispredict and 0 if we predict correctly. So how can we learn this learning problem? So one very simple method is just perform ERM over this class. Just find the best permutation with respect to the training data, and it can be shown that the sample complexity scales like O of d. But computationally, this is a hard thing to do. You can actually prove that under some standard complexity theoretic assumption, it's provably hard to find a close to optimal permutation. So here's another method. So the other method is to enlarge our class and actually consider the class H tilde of all possible functions from pairs of objects to 0, 1. You can do ERM over this very easily. So basically you just need to look at your data and for each pair of objects see which is the most common label and predict according to that. And because the domain is sufficiently small, it's just d squared, you can learn statistically here with the sample size of O of d squared. Okay, so the sample size is larger than the ERM over the original class. It's d squared instead of d, but we can do this efficiently. Another method, which is sort of in between, was proposed recently in a paper by Elad Chazan et al. Essentially what they did is to use a tighter hypothesis class, which is based on positive semi-definite matrices. And they showed that for this problem, you can learn just with d times polylog d examples. But because it's using semi-definite programming, it's a bit heavy. The runtime scales like d to the 4th. So if we summarize the three methods we considered, we can clearly see this sort of trade-off. So just doing an ERM over the original class needs just a sample of d, but you need exponential time. With this semi-definite approach, you can learn with the sample size of d time a polylog factor, and the time now falls to just a polynomial in d to the 4th. And the simple method that I showed previously, where you enlarge it to the class just to the ERM over all functions, then with d squared, you can learn in d squared time. So we have this sort of graph where the time required to learn decreases with the amount of data that you get. So this is a simple example, but again, there is this issue here that these were all just upper bounds. It doesn't formally prove that we really have a trade-off here. And what is specifically missing is some sort of lower bound that shows that for a given sample size, it's really hard to learn computationally under at least some standard assumptions. So our main formal result in the paper is to show that there really is such a learning problem. In particular, it's an example where the instances are just bit vectors, or more specifically pairs of n-bit vectors, and we can show that you can learn this problem with a constant size sample in exponential time. You can be polynomial by any sample size up to log n, but if you get n examples, then your runtime falls to n to the third, to polynomial time. Before showing you the idea of the construction, I should say that a similar question has been considered in previous literature, but those previous works relied very heavily on a realizability assumption, that there is some perfect hypothesis H, and then it's not too hard to think what would be the technique. So it's basically trying to hide the identity of the true H in the examples using some cryptographic technique. So if you could break the crypto system, you can find the perfect H even based on one example. So that's of course not computationally efficient, but the examples also could contain information about the key. So if you get sufficiently many examples, you can recover the key, decipher the crypto system, and get H this way. And that is how you can reduce the computational time by having more examples. But again, this relied very heavily on the realizability assumption, and we want to deal with the much more natural agnostic setting, where we don't assume that there is necessarily some true H. So we really need to use a very different construction here. And our construction still relies on a certain cryptographic tools, which I'll briefly discuss. So the main construction that we'll need is something that is called a one-way permutation. So this is just a mapping from n-bit vectors to n-bit vectors, which is a one-to-one, and is one way in the sense that given some n-bit vector s, it's easy to compute the image of s, but it's hard to compute the inverse. So it's a bit like these one-way car barriers, where it's easy to go in one way, but hard to go in the other way. Maybe the most basic assumption in cryptography is that there are such one-way permutations. For instance, the RSA crypto system is based on such a function. And we're going to use a certain theorem called the Goldreich-Levin theorem, which basically implies that given some W and random n-bit vector R, it's hard to guess the inner product of R and the inverse of W. Okay, so the learning problem that we consider, without going too much into the details, has the following structure. So it's going to use a certain one-way permutation P, and we construct a certain domain over pairs of n-bit vectors S and R and a bit labeled B. All the inner products that we're going to use here are going to be modulo 2. So this is going to be inner product over the GF2 field, resulting just in bits, in zeros and ones. The hypothesis class is parameterized, again, by n-bit vectors W. And I'm not going to go into the details of the construction, but the important point here is that we construct it in such a way that the expected error of each hypothesis reflects how common is seeing a PW in the examples. Or saying a bit more precisely, if we have a hypothesis with low error, where this thing is small, it means that the S that we see would usually correspond to the image of this W. Okay? Okay, and now I'll just go through the basic ideas of the proof. So there are three components, right? We need to show that we can learn inefficiently with a small sample size, and we can't do any better. But for a larger sample size, we can learn efficiently with a much smaller computational runtime. So the first claim, we need to show that this thing is learnable at all with a constant size sample. And the idea is the following. So as I said, the expected error corresponds directly to the probability of S not equal to P of W. Because P is a permutation, this means the probability of W not being the inverse of S. So what would be a good predictor here, one with low error? So again, it's going to be the HW with the W corresponding to the most common inverse of S in our training data. So if we can compute the inverse of these one-way permutations, we just need to find the approximately most common S in the data up to some small additive factor and return H of P minus 1S. And finding the approximately most common element in this kind of discrete distribution is pretty easy and can be shown to, it's possible to do with a constant sized sample, or 1 over epsilon squared if you care about exactly how it depends on the accuracy. Okay, so we can learn this is inefficient, but we can do it just with a constant sample. The second part is to show that we really can't do any better than this. And this is based on the cryptographic assumption that one-way permutations are hard to invert. And basically what we show is that if we can learn with any sample size up to order of log n, then for any fixed w, we can efficiently compute the inverse of w with high probability. And if you're interested in the details, the idea basically is that you can show that with non-negligible probability, one which is polynomially small in n, you can sort of guess some data set of size log n such that the predictor that you learn would necessarily be able to predict, given r and w, the inner product of r and the inverse of w. And this is just with probability 1 over poly n, but just by repeating it poly n times, you boost the success probability and overall get a method to compute the inverse with high probability, and this contradicts the Goldreich-Levin theorem I mentioned earlier. So assuming one-way permutations exist, you can't learn efficiently with log n samples. Third component is to show that with n examples, it is possible to learn in polynomial times. And again, without getting too much into the details, the idea would be, again, to use this trick of enlarging our hypothesis class and allowing ourselves predictors which are not in our original class H. So how do we do it? So remember that we had this intractable method that we just need to find the most common S in the data and compute its inverse and return H of P minus 1S. So this we cannot do efficiently, but it turns out that based on our training data, we can still compute the output, the inner product between R and the inverse of S, for any R in the span of the Ri's that we see in the data. So this is based on how we construct our domain in our hypothesis class, but what this implies is that just by solving a set of linear equations and basically just doing Gaussian elimination, we can compute this inner product for any for any R in the span of our examples, and it's just an n-dimensional space. So if we sample sufficiently many examples, in particular order of n examples, then with high probability any new example that we're going to receive will be in the span of the previous examples, and we'll be able to do the prediction correctly with high probability. And this, the computational complexity is just n cubed, the time it takes to do Gaussian elimination. Okay, so to summarize this work, we had two contributions. So first of all, we showed that there indeed exist agnostic learning problems where provably getting more data reduces the computational complexity of the problem, and it does so very significantly, by an exponential factor in our case. We also discussed several other learning examples where it seems that this phenomena occurs at least on the upper bounds. So actually this sort of behavior seems to be very common. Actually even the setting discussed in Gabor's talk yesterday with the correlation of Gaussian variables seems to have this sort of behavior where there's a gap between what we can get with computationally efficient estimators and computationally inefficient estimators. The main open question is getting the intersection of the two. So can we find some natural learning problem, not an artificial one like what we constructed here, which provably has this sort of behavior? We can actually show that you have both an upper and lower bound, and more data decreases the runtime. And of course, can we leverage this sort of phenomena and these sort of ideas to get new learning algorithms which actually improve in their runtime as they are fed more and more data? So that's it. Thank you very much.
the assumptions from cryptographic assumptions to just sort of empty hardness type assumptions?
Yeah, that's a good question. There has been this very deep paper in the computer science theory community a couple of years ago by Boaz Barak, Benny Applebaum, a few others, where they show that in some sense, if you want to prove hardness result for improper learning, where you're not limited to your original class, then in some sense you have to make a cryptographic assumption rather than like a P not equal to NP assumption. This seems to be the case, but on the other hand, these sort of cryptographic assumptions are very common. So again, all of practical cryptography is based on these sort of assumptions. So I think that's a natural kind of assumption as well.
All right, thank you.
Time for one more quick question. Can you give examples of natural learning problems with upper bounds where the complexity reduces with the sample size?
Well, so the example I discussed earlier was supposed to be like a very natural, very simple yet natural kind of example. So being able to rank objects seems like a natural thing, at least compared to these cryptographic constructions. In our paper, we also have several others, so things related to, say, multi-class classification in a bandit setting where you don't get full information. So explicit problems that have been considered in other papers, things related to detecting certain subsets of entries in random matrices, and so on. So it seems to be a pretty common thing, but again, the problem is always showing that really you have this sort of behavior, so involving also some computational lower bound, and that's usually the hard thing to do.
So basically, the example which you constructed with matching lower bound is the only one you're aware of this phenomenon?
Yes, at least in an agnostic setting where we don't assume anything about the underlying distribution.
Okay, thanks. The poster session will start.